Talk about the XY model, where the energy functional, which is now functional of all the angles at all the different sites, looks something like minus j, the sum over every site and its neighbors, okay? And so there's some cosine of theta of r plus pi minus theta of r, and that's it, okay? That is your energy functional. And then we took the continuum approximation of this energy functional, and we said as long as j is large, all these angles are going to be close to each other anyway, so we might as well replace this by something that looks like E is basically dqx from j over 2 drag theta squared. And when we did that, we found that the Green's function, theta of r, theta of 0, this guy looks something like minus 1 over 2 pi j log of r over a plus 1 over 2 pi j log of L over a. Okay, that's what it looked like. And then we said if we now compute the average of e to the I n1 theta of r plus I n2 theta of 0, this guy goes something like L over a to the power of n1 plus n2 squared with a minus sign over 2 pi j. And then over here, I believe it comes at r over a to the n1, n2 over, I forget, is it pi j or is it 2 pi j? 2 pi j. 2 pi j. 2 pi j. Okay? So that's what it looks like. And this tells you that unless n1 plus n2 is 0, this guy is going to match. In particular, just the average of a single e to the I theta is going to be 0, and that tells you that there cannot be any order. Okay, so it self-consistently checks that whatever you knew from the Murthy theorem is actually correct. Okay?
Yeah, one more thing, this theta r, theta 0 relation. So you can eliminate this a from that.
I don't want to eliminate it.
Yeah.
Because in the end, I want to take the limit L goes to infinity, you see?
Yeah.
So that's why it's important to keep the L separate.
Yeah.
Okay? I don't want to eliminate that. Alright? Good. So then we said what was missing from this was the following, that there is this symmetry, local symmetry, that says that theta of r can go to theta of r plus 2 pi some m of r. And these m's can be some integers that are different at different sites, and then this action is still in there. Okay, so what is the consequence of this? What is the chemical excitation that realizes this symmetry that is not present in that continuum model? And I said that was the vortex. So there's this thing called the vortex, and one representation of it is that it kind of looks like everything is going away from the origin. There are many other representations of this. You can just take this guy and make a global rotation in spin space, right? And for example, it could end up looking like this, which is why it's called a vortex, right? This is what you normally think of as a vortex in your bathtub or something, right? So these two are really the same. They just differ by global rotation. That's all. Okay? Yeah.
So if I have a closed space, then there cannot be a single vortex.
That's right. That's right. It has to be a vortex anti-vortex pair.
And another question is that we said that this went wrong, that we added a 2 pi, then it's a symmetry locally. It's a symmetry of the energy expression that we have written.
Yeah.
Energy function.
Yeah.
But you also assume when expanding like that the theta actually changes smoothly. But in a vortex, if I go very near to the center of the vortex, it doesn't change smoothly. Right? So that is another thing that we assume that goes.
That is true. That is true. But the way of dealing with that, one way you might have of dealing with that is to say that I'm going to keep all the derivative terms, and that should in principle sum up to the cosine, right? In principle. But the problem is that each of those terms is irrelevant. by power counting. So therefore you said forget it and just go with that. But in principle, if you kept all of them, it would reproduce this symmetry. Okay? Alright, then we said the energy of this guy looked something like, the energy of the vortex was something like J over 2, and then the integral over the gradient of this, of the spin, right, squared, and we did that integral, and it came out to be something like, so there was a J over 2, there was a 2 pi, there was a log of this, right? So naively you might think that you don't need to keep this because its energy is huge. Okay? On the other hand, its entropy is also huge, so it can occur at any point of the lattice. So the entropy of this vortex is roughly the log of L squared over A squared, which is 2 log L over A. Okay? So if I write this J as J0 divided by T, right? Let's write it like that. So the energy was really J0. Okay? This energy here was J0. Okay? This J was J0 over T. This is J0. What appears in the action is, of course, J0 over T, which is J. Okay? So if I rewrite the whole thing, then the free energy of a vortex actually looks like J0 pi minus 2t log of L over A. And you can see basically that when t becomes larger than pi J0 over 2, you're going to have these vortices condense in the sense that their free energy becomes less than 0, so they would want to, the system would want to make more and more. Okay? Good. So this suggests that EC is actually equal to pi J0 over 2. And in a certain sense, this is actually correct. Okay? In some particular limit, this is correct. Okay? So that was what I covered last time. Any questions?
So
Yeah.
in that case, you are saying that this quantity expectation value is identically 0
Yeah.
unless n1 is not equal to n2 minus
Minus n.
minus n. So what happens if that is the case? Then is like if I take that particular case,
Then n1 is equal to minus
so
n.
you get a non-vanishing value for
Right,
it.
and that's exactly the power law decaying correlation. Right, so remember we had this case where you had e to the I theta, e to the minus I theta, right? And that was the one that was decaying that power.
So, I mean,
Yeah.
even if, so this is basically the, due to the order parameter lying in a plane, being polar kind of stuff.
Remember, there is no order parameter. The spin lies in the plane.
Yeah.
Right.
Yeah. So in superconductivity also you would have something similar argument.
That's correct.
Because, I mean,
Yeah.
not the order parameter, but
The phase,
spin, yeah.
the phase of delta lies in the plane. Yeah.
Yeah. So
In a 3D superconductor, of course, there's no problem, right? Because there is ordering at low temperature.
No, but even in that case, yeah, you have those spins still lying in the plane.
Not spins. In superconductor, a normal superconductor, in a usual S-wave superconductor,
Yeah.
the spins are inactive because it's just
Not the
similar
spins,
shape.
but those delta, which is C dagger C, let us say, expectation value. That,
See that is C.
sorry, C dagger C dagger.
Yeah.
Yeah. So,
C dagger is a number that has a modulus and a phase.
yeah.
Right.
So,
So it's the phase you're talking about.
yes, yes,
Yeah.
yes.
That's right.
So how do we write a Hamiltonian where we can have such excitations? Because this obviously didn't go right.
In 2 dimensions?
Let us say into that.
Okay, so-
just for this case, let us say.
The very
If
first
you
thing you
have
have to
gone right,
realize.
if we had kept the cos theta, the problem is that we expanded the cos theta and traffic the sim. But if we did a simulation on the full cos theta,
No, that is, it's a different story. The thing is that the superconductor is actually a complicated thing because it doesn't look like this. It has a gauge field attached to it because it's a charged object. Okay? It's actually, the thing is different from whatever we're talking about here. This would actually hold for a superfluid,
Yeah.
Okay, it would hold. So let's not talk about the superconductor, okay, because it's more complicated. It's got other problems.
So what is the analog? But in superconductor you use order pair, right? Sorry, superfluid.
It's superfluid.
Yeah.
It's superfluid. So the thing is that
You have the
you
boson,
have,
yeah.
if it, so imagine that there's a boson,
Yeah.
right? So there's a boson field, and you know that B dagger B dagger of R, B of R is equal to your density, rho of R. Okay, these are operators. Okay, so when there's Bose condensation, what you say, let's talk about 3 dimensions. Okay, when there really is Bose condensation, low enough temperature, then you say your V of R itself is going to be something which I will call square root of rho times e to the I theta of R. Okay, so then you would basically write down a theory that would tell you that, I mean, if you want to write down a quantum theory of the boson, right, in some Euclidean way, you would write something like this: B dagger of R and tau, B of R and tau, right? This is how bosonic coherent states would do in the pattern they grow, right? And then you would have something that would look like, you know, I don't know, gradient B dagger of R dot gradient B of R, right, over some, I don't know, web, something like that, right? This would be its kinetic energy. And then you would put in some term that would look like B dagger of R, B of R, minus rho naught squared. Okay, this would say that density fluctuations are expensive. Okay? You know, the density is something on average, and the fluctuations are expensive. Okay, now the point is that if you assume that this degree of freedom, as shown here, is actually expensive to perturb. So if you write rho as rho naught plus delta rho, and then you integrate out delta rho fluctuations, you end up with, and of course you will end up with it in 2 plus 1 dimensions. Okay? That is just the statistical mechanics. This would be the action for the statistical mechanics of that theory, as long as no vortices were present. If a vortex was present, then you'd go back in here and put in the vortex and solve for it. And you'll find that at the core of the vortex, the density has to go to 0. Okay? And so that will provide what is called the core energy of the vortex in a superfluid. Okay? All right. So, today what we're going to do is we're going to find one way of taking this seriously. The question,
Okay,
yeah.
probably it's for Ashok. So
Yeah.
what is the continuum analog of this vortex? Is there such a thing or?
Yeah, there is a vortex. Yeah.
Abelian Higgs model has
Abelian Higgs
vortex, yeah.
But of course, you always have to have some cutoff, right?
But okay, what is the observable like in which you calculate like let's say count the number of vortex density or something?
It's a topological quantum number, right? In the
Okay.
Abelian Higgs model.
Oh, okay.
Does it have a charge?
It's a topological charge. Okay. Because it's winds around.
Yeah.
So the winding number
Yeah.
is the charge.
Yeah. But in 3 plus 1, in 2 plus 1, actually it will be some loops, right?
Yeah.
It will be some lines
Yeah.
of vortices.
So we do have vortices in superconductors.
Yeah, you do, yeah.
But they respond to this magnetic field, whatever flux lines we have in the background.
Correct.
Right. So the phase of the superconductor and these magnetic flux background, they get related somehow.
Absolutely.
Right, but if we were so that those fields immediately come into the picture if we were to make some measurement or do something about it.
Well,
But-
that's what I was saying, that the vortices in a superconductor, unlike these vortices, they actually have finite energy. Okay, their energy goes something like this, but the length that appears there is not the system size. Where is the penetration depth? Okay, so it's a finite energy. So the long distance physics, I mean, physics at distances much longer than the penetration depth, is actually not the same as that of a neutral superfluid. Okay, so it's quite different. Especially in two dimensions, right? These vortices actually have a KT transition, right? If you really measure the superconductor, operationally you might see a very sharp crossover that looks like a DKT transition, but in reality it's not. In two dimensions for a superconductor, there is no DKT. Okay?
But if we had a superfluid
Superfluid will have a transition, for
and
sure.
whose order parameter, let's say we calculate self-consistently somehow. So you were
In
saying
two dimensions or in three dimensions?
in two dimensions.
Two dimensions, there won't be any order.
No, okay. The expectation value of the okay, average B diagram, let's say.
It will be 0. It's a continuous symmetry, you can't break it in two dimensions. Okay? It will be 0. There is no superfluid. There is no true superfluid in two dimensions. There are these power law correlated phases.
Yeah.
Okay? So it depends on what you mean by superfluid, alright? If you mean something that has a stiffness, then yes, it exists. If you mean something in which the bosons are condensed, it doesn't exist.
No. So for any finite interaction, those there would be excitations above the condensate. So I mean they are not all condensed in the ground state. If that's what you mean.
No. I'm saying there is no condensation of bosons in two dimensions. That's what I'm saying. Okay? At any non-zero temperature, there is no condensation of bosons. Okay? We can discuss this because I know you've been trying to get at this point for a long time. So let's have a private one-on-one conversation and we will hash it out. Okay? Good. Alright, so now what I'm going to do is I'm going to show you one way in which you can essentially exactly solve this problem. Okay? And so the very first step is to take this model and do something called villainize it. Okay, so Villain was a French physicist who actually described a different way to look at a model that has all the same symmetries as this model. So remember what the symmetries are. First of all, there's a global U1 symmetry, continuous global U1 symmetry. Secondly, there's this local symmetry that says that if I add 2 pi times an integer locally to any theta, it shouldn't make any difference. Okay, so what he did was he said that his partition function is going to look like this. So there's going to be some product of integrals over d theta. Okay? Alright, now I'm not even going to put the limits. Because as we discussed the other day, you can make the limit 0 to 2 pi or you can make them minus infinity to infinity. It doesn't really matter. Okay? So now he's going to, in addition, on every link, he's going to define a integer. So let me draw the Alright, so let's say this point is R. This is R plus EX. That is R plus EY. Okay? Now on this link, I will define something called MX of R. Okay, and on that link, I will define something called MY of R. Okay, together they make a vector. So on a lattice, any vector has to sit on the links. Okay, that's the natural place for a vector to sit.
I just want to go ahead and answer. So why we don't describe this local symmetry, local discrepancy in symmetry? Is not a gauge. Why is not a gauge?
It's a sort of a gauge, but the problem is that the gauge field is discrete. It takes integer values.
Right, because
You can certainly think about it as a gauge. Nothing wrong with that.
right, because the way we are introducing these m's,
Yeah.
they are like a.
That's how you would talk about a gauge field, exactly. But instead of having continuous values, it has integer values.
I agree, but so what I'm saying that in some way we are actually introducing a gauge field to handle that problem.
Correct.
Is that right?
You can think about it that way. You can certainly think about it that way. Okay? Now, it might make you feel cooler to think about it as a gauge field. Okay? To me, it's just, another model that has all the same symmetries. Okay? So what I'm going to do now is I'm going to sum over these integer fields at every side. So in other words, the configurations now include not only the angles at every side, but also all these integers on every link. Okay? So I have vastly expanded the space of configurations.
Sir, these integers and these m, no?
Sorry?
These m's,
These m's are sitting on the side.
Yeah.
So let's be very careful, okay? These m's are sitting on the side.
Okay.
Okay, and on every side I could make a different m. These m's are sitting on the links.
Links,
So
okay.
they're vectors.
Yeah, but why did you, I mean, we just needed, a scalar m rather than a vector m as such. Right?
Wait.
Yeah.
Okay. Wait. I haven't even done the action yet.
Yeah.
So, alright. So you have something that looks like this. And then I'm going to sum over r and the two different directions. Right? And it's going to look something like this. So let's write theta of r plus ei minus theta of r minus 2 pi mi of r squared. Okay? That's the entire energy functional sitting there. So remember, I've done two things. I've changed the energy functional, and I've also expanded the configurations that I'm going to be summing over when I do my partition function. Previously, all I had was thetas, right? But now I have thetas and I have m. So it seems like I've added some complications to this model. Okay?
Well, I mean, are you just adding this thing, or are you expanding this thing, substituting theta or?
No. I'm not expanding anything. I'm just saying that this model and that model have the same symmetries.
Okay.
That's all I'm saying. And remember, we have this idea now from this conceptual RG that we did earlier on, that as long as the symmetries are the same and as long as the dimensionality is the same, then the critical behavior should be the same. Right? So we have that idea. So based on that idea, we say it doesn't matter if we take this model or we take that model, as long as they have the same symmetries. So let's just verify that they have the same symmetries, right? And so indeed, if I add some 2 pi m to this guy and some other 2 pi m to that guy, I can always absorb it into this m sub I, right? Because in the sum over all configurations, there will be one in which there will be those extra phases. Okay?
So these m's are continuous value. These m's
No, they're discrete integers. That's why I'm putting a sum over them. They're not even being integrated, they're integers. Otherwise, I would have too much, right? If these were really continuous, then I would say that locally I can make any change whatsoever to all the thetas. If I could do that, then I could make all the thetas equal to 0 at every side, and then my model would be gone.
Yeah, but then
So m's cannot be continuous.
how can you absorb the difference of this m between two sides into that if that m was discrete?
This m is also discrete. Right? Because I can only change this by u phi times an integer.
Okay.
Right? That was the symmetry. That was a local symmetry. It's a discrete
So this
symmetry.
2 pi n.
Okay?
Sir, I got again confused that
Yeah.
m in the exponential,
Yeah.
these are the side dependent m's.
No.
No.
Oh, okay.
It's n sub I. It's a
It will be
vector.
better to use some other symbol.
mx and my.
Oh, okay.
These and
Okay. Oh,
Okay? This reminds me of that cartoon where Einstein is seen to be writing, says, this doesn't look right. No, this also isn't right. And so on. Okay. This is at that level now. Okay? So, you guys get it? So the symmetries are all the same. Okay, it's easy to verify. First of all, if I rotate all the angles by the same amount, this is a difference. So obviously it's a symmetry. On the other hand, if I change this, one of them, by 2 pi, since this sum involves all integers, after the sum, you just rearrange it. You've just rearranged the sum. That's all you've done.
So you are summing over all possible.
It's just sum over all length from minus infinity to infinity on every link. Okay?
So it integrates back to the middle, or you cannot do that.
Z remains invariant.
It does not integrate back to the original.
I'm not sure what you mean by integrate back, because this set of configurations is much larger than that. So you're saying somehow if I sum over all these configurations here, what will it become? It becomes some periodic model, okay? It will become some model that will have this term, but it will also have all possible other periodic terms in the action. Okay? That's what it will boil down. It will have cos of theta minus, theta separation of the neighbors will have cosine 2 times that, cosine 3, 4, everything.
Is there an I there?
Where? There?
Like,
This one?
exponentiation, is there an overall iota I there?
Why? It's statistical mechanics. There's no I. Okay?
So after changing one of the theta y to pi, so the links will also, the m values on each link will also change.
You can do that if you want, but you can also say that I'm summing over all possible m values. So when I add 2 pi to this guy, all I'm doing is I'm rearranging terms in the sum. I'm just shifting the sum by 1. Right? I can define a new n prime if you want. So supposing I make this theta of r plus ei plus 2 pi, let's say. Okay? Then I'll just define an mi prime, which is the old mi minus 2 pi. The range of that summation is also minus infinity. So it's nothing has happened. Okay?
Okay, now.
Yeah.
Yeah, it's confusing because the energy functional is now not invariant under 2 pi summation, or?
No, it is.
It is?
No, it's not the energy functional that is invariant. It's the entire sum that is invariant.
Yeah, I mean the G will, the total G will be.
The Z will be invariant.
G will be invariant, but the
Z will be
energy
invariant.
functional is not.
That's correct. This guy itself, of course, will change
Yeah.
for a particular value of mi. But the partition function is invariant.
In principle, you could just sum over mi's and define a new energy function, right?
You can.
In terms of theta.
You can. But I want to keep it this way because this is very convenient. Okay? So all you should really worry about is, does this have all the same symmetries as the original one? The answer is yes. Okay? Good. So now,
But at the partition function level, not in the action.
yeah, at the partition. That's right. Yeah, at the partition function. And remember, when I'm going to make correlation functions, I'm just going to take correlation functions of e to the I theta, e to the minus I theta, things like that. Okay? I'm going to take correlation functions only of things that satisfy this invariance. Okay, good. So now the reason this is very nice is because it's Gaussian. Okay, that's why Milan did this. And so now let's continue and analyze what happens. All right, so now we're going to make what's called a Hubbard-Sturtowner's transformation. So what is this? Basically, you just decouple that Gaussian and make it linear. Okay? So if you have something like e to the minus, let us say, I don't know, let's call it q squared, right? I'm going to introduce an auxiliary integral. So let's call it j over 2q squared. All right? I'm going to introduce an auxiliary integral that looks something like this. So let's say I will introduce a b, and then e to the minus b squared over 2j plus or minus, it actually doesn't matter, I b cubed. Okay? If I do this, you can just do this integral up to some factor of, square root of pi's and j's and things, which whenever I take correlation functions, they will all vanish anyway, right? So we don't care about those factors. All right? So now I want to introduce yet more variables now. So now my partition function looks like this. So there's going to be an integral over the thetas. Now there's going to be an integral over a vector field B. And there's going to be a summation over all these integer valued vectors. Okay? And then it looks something like this. So there's a summation over R and I, right? And then I'll have something that looks like minus, okay, so we'll put the minus summation over r and I, okay? So I'll have a bi squared over 2j, right? And this bi is of course a function of r. This bi lives on a link. Okay? There's that, and then there's this plus I bi times theta r plus bi minus theta r minus 2 pi mi of r. Okay? Good. Now why did I do this? Because now I want to integrate out the angles. These angles now can be completely integrated out. Because it's e to the I something times the angles. Right? Okay, so let's ask ourselves, supposing I set a particular site R, what are the B's that are talking to it? Okay, so here's my site R. So what are the B's talking to it? Well, it will be this minus that, right? Sorry, this minus that times the Bx here. So these two bonds, the theta of R appears with a minus sign. Because it's this minus that and this minus that, right? On the other hand, in those two bonds, it appears with a plus sign. Okay? So if I take this, if I rearrange this sum here, and I take theta of R, so it will be the exponent, it will look like e to the I b theta of R, there's a sum over R, and let's see what comes out here. Okay? So there will be a minus of bx of R minus by of R, right? That's the right and the upward pointing bonds that we talked about. On the other hand, there will be something that looks like plus bx of R minus dx plus by of R minus dy. Okay? This is the bond, this one is the bond to the left of R, and this one is the bond below R. So just stare at it for a second and make sure that you agree with what I've written there. Okay? Yes?
The first two are minus because of the minus sign outside.
No,
Okay.
it's not because of the minus sign outside. It's because here, so inside the action, remember, I have to have e to the I. So let's see what happens with bx of R, right? Bx of R is multiplying theta of R plus dx minus theta of R minus 2 pi and x of R, correct?
Yes.
It's this minus sign I'm talking about.
Oh, okay.
Okay? Now if you look at this guy here, if you think about the site R and you draw these bonds in the forward and upward pointing directions, you will see that what this is saying is that this plus this is equal to that plus that. So that's the lattice version of the divergencelessness of B. Okay? So I can write this condition by saying the divergence of B is 0. This is what I would write in the continuum. But on the lattice, this is what it means. Okay? Good? So this is a vector field. It's a continuous vector field that at every point on the lattice satisfies the divergence free condition. Okay? Now if this were the continuum, how would I solve this in two dimensions? It's very easy. I would say Bi is epsilon ij bj phi. Okay? In the continuum, if this phi was a smooth field, it would automatically satisfy the divergence free condition.
Where did you get equal to 0 condition?
Where did I get equal to 0? Very good. So now remember, I'm integrating over d theta, right? And I made the limits of integration of d theta minus infinity to infinity. So this is like a representation of a delta function. Right? E to the I theta times something integrated from minus to plus infinity. That's good. I forgot to mention that. Okay. So now I'm doing all the theta integrals. And the result of doing all the theta integrals is to find this condition at every lattice site. Okay?
From
Yeah.
this condition, it's not necessary to integrate theta from minus infinity to plus infinity. Right?
Actually,
It's the exponential of I times a number.
no, the point is this. If that number were an integer, then from 0 to 2 pi, if the number were forced to be an integer, you could say the integer was 0. But if the number were not forced to be an integer, because now I'm doing Habermas economics, right? I'm doing an integral to b.
So b is continuous, so it doesn't. It has to
b is continuous, so I have to do the integral from minus to plus. Okay?
And you are allowed to do minus to plus infinity because it doesn't matter. You have taken care of by
Yeah, it just adds more copies, right? So it doesn't matter. All right? So now we have eliminated the theta, but we still have this constraint, and we want to satisfy the constraint on the lattice. How do we satisfy the constraint on the lattice? Well, let me satisfy it in the following way. So let's call this site R, right? This is the site R plus Ex. That's the site R plus Ey. This is R minus Ex, and this is R minus Ey. This site, which is sitting in the center of the plaquette, I will give it a name. I will call it capital R. Capital R is this dual lattice site that's associated to the lattice site. Okay? The dual lattice site is always sitting in the center of the plaquette. Okay? Fine? Alright. So, if this is the dual lattice at capital R, this will be the dual lattice at capital R minus Ex. This will be the dual lattice at R minus Ey. And that will be the dual lattice at R minus Ex minus Ey. Okay? Now I define my B in the following way. I have now a continuous field capital Phi, and this field lives on the dual lattice sites. Okay? So I'll define it like this. I will say that it's always, as I go around this site, it's always the guy that's more counterclockwise than the previous guy. Take this difference. Okay? So on this side, I will say dx of r should be equal to phi of r minus the phi of r minus dy. Okay? So if I'm pointing along that bond, I look at my left minus the right. Similarly, if I'm pointing along that bond, I will say dy of r is equal to phi of r minus dx minus phi of r. Okay? So that's how I define it. And now similarly, this guy here, of course, is going to be this minus that. And that guy will be this minus that. Right? And now you can see that this combination will vanish. Do you see that?
I'm sorry, why did you introduce phi?
Because I want to do the lattice version of this. In the continuum, this is what I would have done, right? To solve that condition. Because you see, instead of integrating over a vector field with a constraint, I would rather just solve the constraint and integrate over whatever remains.
So you define B as a curl of a scalar field kind of a thing.
Well, curl is a three-dimensional concept, but yeah, you can say it's like z hat cross gradient.
Huh.
You can call
Will
it
there
that.
be division by some unit length, like the lattice length or something for this? So there is a del finding.
This is the same thing. That thing written on the lattice is this. Okay?
And he is worried about the 1 over a that accompanies tail.
Is there a 1 over a kind of a thing also?
This is derivative is 1 over a times.
It's not, it's all in my lattice spacing is 1.
That is normal.
I'm not doing any RG now. Okay, I will do RG later. This is all the lattice spacing.
I was just counting dimensions.
Also,
This is just a definition of
Everything is dimensionless.
You could absorb anything. This is the definition of
Everything is dimensionless. Okay?
also you are getting this divergence 0. Will you get any vortices? Shouldn't this diverge?
The vortices are not going to be in this. They're going to be something else. Okay? So remember, if you think of A the gauge field as this M, right? If you think of that, then you know that the guy that appears naturally is like the flux of that gauge field, right? That's the gauge related object. That is going to be the vortex density. Okay, it's that guy that codifies the vortex. Okay? So, look, it's very easy to see that this divergence is satisfied because this guy is this minus that. So this appears with a plus sign, that appears with a minus sign. Now I want to add this, but there, that appears with a plus and that appears with a minus. So this guy is already cancelled. Okay? And so on. You just go around the circle, you will easily figure out that this is satisfied. Okay, at the last level. So this thing is going to be 0. Okay? So
we need the arrow, right? The arrow is important.
yeah, so remember, anytime you have a vector field, you have to have an arrow. So my definition of the arrow is defined like this. So it means that I always go either to the right or upwards. Okay, so if I'm going that way, it will be minus. This guy will flip signs.
So Bx of R actually means that it lives on R and R plus Ex
Correct, it lives here.
going in the positive.
Okay, it lives here. It lives on the link. Okay, the link itself tells you what direction it is because you have to choose the convention where it's always going one way. Okay?
So then I can solve for phi and I'll find that it will close on itself.
Phi,
From
the
this
thing
relation.
is that phi is a function. So it has to close on itself. Right? So if I step from here to there, to there, to there, to there, looking at all the differences, they have to be 0. It's like a potential, right? So it has to close on itself. But that in turn implies this. Okay?
But this defines phi only up to an overall constant shift.
This defines phi only up to an overall constant, but since I'm integrating over phi from minus infinity to infinity, okay, I actually don't care. Alright? Yeah.
So are these terms are like the difference between the angles of two theta is different?
So, what do the m's actually mean? So the m's, you should think of them as meaning the following thing. Supposing I have a vortex configuration, okay? So let's think about a vortex configuration. Okay, so this theta, let me define it as pi by 4. Okay, this theta is going to be 3 pi by 4. That theta is going to be minus 3 pi by 4. And that is going to be minus pi by 4. So then I will say that among all those configurations, which ones are dominant? Okay, when the angular separation is less than pi, the dominant configurations will have m equals 0. So m will be 0 here. M on that link. Okay, if you choose m to be non-zero, then that Gaussian will be much suppressed compared to the m equals 0 contribution. This will also have m equals 0. This will also have m equals 0. But this guy will not. Because you see, this is 3 pi by 4, and this is minus 3 pi by 4. So the difference between them is 3 pi by 2. That's closer to 2 pi than it is to 0. So here m will be 1. Okay? So the curl of this m, okay, in other words, what you would normally think of as the flux of a gauge field, right? That guy actually knows whether there's a vortex there or not. In this sense. Okay? That's what m means. Okay?
What is the combination of 0 and 1? It will be 0 and 1.
So the point is that here, I want this to be as small as possible because it's a Gaussian, right? So I ask, what are the dominant terms in this sum? Right? What are the most important terms? The most important terms are the ones in which this number is as small as possible. That defines for me some particular value of m on every bond. Right? And that is the meaning of that.
So once you integrate out theta from that action, you just end up with the delta function, with the constraint.
Yeah.
But there is no coupling between B and M directly.
Well, there is, right? Because the B's were actually multiplying not just theta minus theta, but also this.
I see. Yeah.
Okay? And that's turning out to be, that's going to turn out to be very crucial.
I see.
Sir, one second. To calculate the divergence,
Yeah.
so we have to calculate Px at R, the 4 points, corresponding 4 points.
This.
Okay.
Right? This is the lattice divergence.
Yes. No, okay.
I'm claiming that given that expression for what the B's are, if you put it in here, you will find 0.
Okay.
So it will be automatically satisfied. Okay?
So there, this M is conjugate to B, and after you integrate out the theta, and then what you do, you minimize it with respect to.
What do you mean by conjugate?
I mean, they have a product kind of a coupling. So
Okay.
yeah, so if you take derivatives with either one of
So let's try to write it in the continuum and see what happens, right? That'll give us an idea of what's going on the lattice. So we've integrated out the theta, and then we have now reduced our B to look like epsilon ij dj phi, right? So in the continuum, what would this thing look like? So the B itself would look like this, right? So when I square it, it's actually going to look like, so the action is going to look like now the sum over the dual lattice side, right? It's going to look something like gradient of this phi squared over 2j, right? That's what the B squared looks like, right? Bx squared will be d by dy of phi squared, and dy squared will be d by dx of phi squared. So just hang on. Okay, there's that. But then there was also this term here. There was this term here, right? So it was something that looked like minus I, and then there was a 2 pi, and then there was this m, right? And this m was a vector, right? So let me write it as an mi, right? Epsilon ij dj phi. This is the continuum lattice, okay? All this can be written on the lattice without ambiguity. But I'm just doing it like this to make it clear what's going on.
No. So there is already an I for the lattice. So there, you by this I you mean component of M, right?
This is a component.
Right.
Okay, so this is again ma squared, mb squared, and mc squared. Okay?
Then there's V dot grad theta.
Sorry?
V dot grad theta.
This is
But theta is integrated.
there's no, the theta is gone. I've integrated it out. That's how I got the divergenceless condition, right? It's just this term now that's left. And now I'm re-expressing B in terms of that. Okay? So what this basically gives us is if I integrate this by parts, which I can do on the lattice, which I will do in a second. When I integrate this by parts, this basically gives me a plus I 2 pi phi, and you will allow me to write it like this, even though it's a bad notation in 2 dimensions. Okay? Fine? That's what it looks like.
So this M do behave like some sense.
So M, you can think of M is like A, and this is like F.
So it do behave like a gauge potential.
Yeah.
But M takes integer values, right?
M takes integer values.
So the square of M is
It's an integer valued gauge field.
Yeah,
The
okay.
curl of M is also an integer.
Yeah, but if one shouldn't think of it as a continuum, right?
No. Definitely not.
Yeah.
Definitely not. No. Okay? Question? No. Alright, so now let's do it on the lattice, right? So let's ask ourselves, supposing I take a particular phi of r, now I have to do this as well. So this is r plus ex plus ey, right? Good? So if I take a particular r here, right, there's a phi of r, what m's does it talk to? Okay, it's certainly talking to this m, this m, this m, and that m, right? That's who it's talking to. Okay, now for these two guys, it appears with a plus sign because it's this minus that. And now here it appears with a minus, sorry, here also it appears with a minus, with a plus sign because it's this minus that. It's always the guy to the left of the bond minus the guy to the right of the bond. So it's this minus that, this minus that. But here and there it appears with a minus sign. So basically this whole thing looks something like minus I to pi phi of a particular r times, okay, so it looks like the mx of r plus my of r plus ex minus mx of r plus ey minus my of r. Okay? So these two bonds appear with the plus sign, those two bonds appear with the minus sign. Okay? And that is exactly the curve. Okay, you can see that this is like minus d by dy of mx, and this is plus d by dx of my. Okay? So that's what it is. Alright? Good. So let me call this number, since it's naturally associated with the plaquette, I will call this number q, and of course, it lives on the plaquette. Okay? And if you want, this is the only gauge invariant part of M. Okay? Fine? Alright, so now life is becoming simple once again. So we have some giant complexity in the middle, but now it's very simple.
Just fast. So what was the gauge transformation on M when we wrote down the first?
Right. So remember that there was each theta of r would go to theta of r plus 2 pi n of r, right? So the gauge transformation on mx of r, for example, would be mx of r plus n of r plus ex minus n of r. Something like this would be the gauge transformation. Okay? All right?
This quantity takes care of that.
This quantity is invariant under that. Okay? Because it's the curve. Okay? Good enough? Now this time you really guys, you have to go back and work it out, because there are steps here that I'm not completely working out, but you have to go back and fill them in. Okay? And somebody tells me that I should call some people to the board and ask them to explain in the next class. Okay? And I know who I'm going to ask. You know who you are. Okay? The guys who are always asking questions will be the first to be asked. And also people who have never asked a question will also be asked. Okay, so. Alright? Good, so please go back and fill everything. Alright, so now, let's see what happens. So what do I have now? So I have this partition function. Let me write it down. Okay, so what is it? It's some integral over this field now, right? It's a continuous field. And there's a summation. Okay, I'm going to write the summation over Q, because that's really only the gauge, that's the only gauge invariant part of this n. So it's now a integer that's sitting on every plaquette. It's not a vector anymore. Okay, it's a scalar, because the vectors would sit on the links and the scalars would sit either on the sides or on the dual lattice sides. Okay? So it will look something like this. e to the minus the sum over r and I, right? Or let me call it mu. Okay, so it will look like basically phi of r plus mu minus phi of r squared over 2j, and then there will be a plus or a minus. It actually doesn't matter what. Okay, I, and then there's a 2 pi, and then there's a phi of r, and then there's q of r. Okay, this is what you have. Now there are several different directions in which one can go, but let me take the shortest path to where we want to go. But first, you guys agree with this? Okay, so in general, of course, the summation is really over all m's, right? But I'm assuming that given some set of q's, right, the summation over m's is the same for any given set of q's. That's what I'm assuming. So I can that sort of cancels out. I don't need to know about the summation over m.
In other words, the rest of it does not contribute to the action.
It doesn't contribute to the action, but also the degeneracy that it contributes is the same, regardless of the value of q. Okay? Good. Now, I'm going to introduce one more term in the action. So, I've already given you the reasoning behind why this q should be thought of as the vorticity, right, of the original one. Right? Remember that logic of, what is the dominant configuration and so on. Right? So I'm going to now assume that this q of r is restricted to 0 and plus minus 1. And furthermore, because in a square lattice you can't really put more than one vortex if you don't look at it, right? So then I'm also going to put in an extra term, which looks like something like mu times qd squared of r.
So you're assuming this q, this limited set of q,
Yeah.
are the lowest energy excitation. So
That's correct. That's what I'm assuming. Now what is this guy?
But the
This is
sum
like-
itself includes all q, right?
The what?
The partition function.
The partition function includes all.
So there is some kind of saddle point.
No, it's not a saddle point. I'm now introducing some extra terms into the action by hand. Okay? So, in fact, let me put it this way. First, let me introduce this. Okay? What is this? This is like f mu squared. Okay? Remember that if you were doing some RG, such a term would be generated because it's gauge invariant, right? So anything that's gauge invariant should be kept from the beginning as the usual RG thinking, right? So let me put that in. Okay? Once I put it in, you see it makes it more expensive to have larger values of q. Okay? And therefore, I claim that from here, I go backwards and I say, okay, now I'm going to restrict myself to q equals 0 or plus minus 1. I'll tell you what happens if I include more q's, okay? In just 5 minutes, you will see. It doesn't make any difference. Alright? Good? Now, I will also claim that such a term actually was present in the original XY model, but not in the Villan model. Okay, the original XY model, it actually is expensive to create a vortex, exactly because of all those short-range costs that go into the vortex. It actually is expensive. Okay, and so this, you might want to call it the core energy of the vortex. Okay? So I'm just introducing some core energy. Okay. Now I can solve this model when this core energy is high. Okay, so let me write down the action. What does it look like? So now my action looks like the sum over r. Okay, so I'll write it in shorthand, okay? Without writing everything on the lattice, right? And then there will be this plus or minus 2 pi I q of r phi of r. And then there's also this term here, okay? Mu q of r squared. Okay? Now remember, it always appears as e to the minus s. So in the case when mu is large, I will be able to solve this point. Okay, let me introduce the following object, which is called the fugacity. So y is e to the minus mu. Okay, actually it's e to the minus beta mu. Okay, but remember we are setting t equals 1 throughout here, right? So this is the fugacity. Okay, this is a word from thermodynamics. All right. So now if we restrict it to 0 or plus minus 1, then at every site on the lattice, I can expand this guy. So what does this partition function look like? All right, so I have this d phi, right? That is obviously there. And then I'm going to write down this term here. So there's a 1 over 2j integral. Well, okay, so let me write the sum. But I'm going to write it like this, okay? But you understand what this means. And now I'm going to, these other terms that are present are completely local, right? They only depend on capital R. They don't make a connection between R and its neighbors. So I can expand them out for every R. So I'll write product over R, right? And I'm going to look for the terms that have q equals 0 or plus minus 1. So what will I apply? So it looks like 1. That's the term with q equals 0. Then there will be a term with q equals 1 that will look like that. Right? Then there will be another term that looks like, and I will end it there. You agree? Because when q is 0, this term doesn't contribute. So it's just a 1. Okay? When q is either plus or minus 1, it will be e to the minus mu, and that's what I'm calling y. Alright? Now remember, this y is very small, because I'm assuming that mu is large. Okay? So this y is much less than 1. Given that, I can re-exponentiate that object there. And I can rewrite it then as you guys agree with that? Because this is 2y cosine 2 pi phi. If I take the log of that, right, log of 1 plus 2y cosine 2 pi phi, it will just come with a plus sign up there, so there's a minus and a minus. Okay?
So if you just did restrict yourself to equal to 0 plus minus 1 without going into mu, so you would still have gotten that cos phi term.
Right, but I would not have gotten the y to be small.
Yeah, but I don't even understand why. Why you need...
Why is y small?
Not
Because I want to do some perturbative algebra.
Yeah, but your argument on like bringing the stiffness for Q, that part I could not.
So the point is that in the XY model, right, there is a core energy for a vortex.
That you can very well compute. I mean, you know that is something.
Right. But what I'm saying is that there's a logarithmic part of the energy, and then there's a core part of the energy. Okay, so in other words, you can take the log part from the long distance behavior of that. Okay, and you extrapolate it down to 8. All right. So you get something that looks like what we had before, right? There was some j over 2 or pi j log of L over 8, something like that. What I'm claiming is that in the XY model, there's actually an additional cost beyond that. There's a constant. It's not logarithmic. It's a constant which also is proportional to j. Of course, everything is proportional to j. All energy is proportional to j. So the actual energy for vortex has the log part and it has this extra part. This extra part is what I'm calling the nu. Okay?
So, but where is that extra? Where? How can I see that extra part from in the original cos kind of model?
Right. So let me just repeat what I said. So you take your long distance behavior of this vortex, right? It has some log. Extrapolate it down to 8.
8.
Right? But then there's an extra contribution due to the very short distance behavior which is not captured by just the continuum. Okay? So what I'm saying is that, look, okay, let me put it this way. Don't worry about where it comes from. Okay? Generically, if such a term is allowed, I should put it into my RG. You agree with that?
Yeah.
If it's relevant, I should put it in. Right? I don't know yet whether it's relevant or not. But I have to put it in. Right? But it's also true that in the XY model, the actual nearest neighbor XY model, this guy has a value that can be computed. Okay? Fine?
Yeah. So I can just arrange the spins in a vortex and compute what is the energy.
Correct.
And you're saying that that would differ from this log at
Correct.
shorter distances.
Correct. Correct. There's some extra short range energy. Okay? But really, I mean, because it's going to be generated by RD, you have to keep it. Okay? There's just no alternative. And it is going to turn out to be relevant in some regime. You better keep it. Now, what would have happened if I had kept higher powers of this yield 2 alpha? Right? What would have happened is that I would have had to keep
Twice.
cosine of 4 pi phi and cosine of 6 pi phi and things like that. Right? That's what I would have had to keep. Right? So that's what it is.
So those are 4 pi vortices and they have more windings.
That's right. They have more money. Exactly. Okay?
And I have got another related question.
Yes.
So when you went from this XY model to the Villain form,
Yeah.
there you're saying that if you summed over the vector ends, right?
You would sum over the what?
The vector, the new m.
Yeah.
You
Yeah.
would not only generate a cos, but you will generate higher cos with higher 2 theta, 4 theta, something like that.
Yeah. You
So,
will.
yeah, so don't they mean that you would have higher vortices?
No, cos 4 theta and cos 2 theta are not vortices. Right? They're not vortices.
No, I'm saying that one thing is periodic. So just
Yeah.
cos theta I minus theta j is periodic under 2 pi.
Yeah.
The other thing is periodic under pi rotation.
I know, but there's already the first term, that is cosine of theta I minus theta j for the nearest neighbor. So the overall thing is still periodic only under 2 pi. Right? Just because one piece of it is periodic under something else doesn't mean much. Right? So it doesn't change the periodic structure of it just alters the nearest neighbor energy and so on. It alters the short distance properties of the XY model. Okay? Good? Alright. Yeah.
So this is the core energy, okay? So
This is the core energy,
you have to make a bigger loop and then you can contribute.
Bigger loop.
So this is for only one placket.
Yeah.
It comes from one placket. Okay, but can you have 2 plackets joined and then
Yeah, but that would just correspond to the sum of the vorticities of the 2 plackets.
Okay.
It's completely linear,
Okay.
right? Because that bond in the middle will cancel. So there's this nothing beyond 1 placket. Okay, you can just add up plackets and get it.
The energies of these charges, they don't depend on the sign.
They can't depend on the sign, right? Because the system itself doesn't pick whether it's a vortex or an anti-vortex. Right? How is the system going to pick?
That's why we don't have any Q.
That's correct. You cannot have any terms that are odd in the Q. Right? Alright? Good? So this model is actually the Sine-Gordon model. Okay, so at the most basic level, it's very easy to analyze. Because what we're going to do now is, let's rescale this phi. Okay, let's call 2 pi phi our new field. Okay, so let's define a phi, or let me define a phi which is 2 pi times this capital Phi. Okay, so then this action looks like 1 over 4 pi squared j squared gradient of this phi squared minus 2y cosine of phi. Why am I writing it like this? Because I want to compute the scaling dimension of cosine of phi. Okay, so remember, we computed something very much like this. When we were looking at the e to the I theta, e to the minus I theta correlation, right, we computed exactly such a quantity. So, what was that? So we said if the action looks like 1/2 j grad theta squared, then e to the I theta of r e to the minus I theta of 0 would go like a over r to the power of 1 over 2 pi j. Right, remember that? This calculation we did last time. Now, that tells me that the dimension of this you guys agree with that? Why? Because this power basically has two of these guys here. Right? So I want to compute the dimension of this operator here in that theory. Okay? So what will that tell me? Well, that will tell me, is this really 2 pi j over here? Or is it pi j? Can you check?
2 pi.
Sure. 2 pi j. Okay. Alright, so the dimension is 1 over 4 pi. So let's work it out over here. Right, so this quantity here, I will call this some j tilde over 2, right? Because I need a half there. Right, so j tilde is 1 over 2 pi squared j. Alright? So the dimension of cosine phi, which is the same as the dimension of e to the I phi, is going to be equal to 1 over 4 pi j tilde. Okay, just by transcribing stuff. Right? So this j tilde, I know what it is. So this looks like pi j over 2. Right? Now something is wrong. I think it should be pi j. It shouldn't be pi j over 2. Ah, I know what's wrong. Here's where it's wrong. This is 8. Okay, because there was a half here. Right?
It should be j, this is not j squared, right?
It should be j. Correct. Good. So this is correct because of there's another factor of 2 and then there's a 4 pi. So that's good. Okay, so j tilde is good. Alright? So the dimension of this guy is pi j. Alright? So by power counting, the total dimension of this guy, y times that, should be equal to 2. Because it's 2 dimensional. So the dimension of y is 2 minus pi j. Okay? So what is this telling you? It's telling you that whenever pi j is bigger than 2, this y has negative dimension, so it's irrelevant. When pi j is less than 2, this guy is relevant. Okay, so this is really what we want, right? And remember, what does this really mean? It means that the critical point is going to be at 2 equals pi j. Remember, it was that, right? So this tells you that PC is pi j over 2, j naught over 2, right? This is exactly what we got from the original estimate. Right?
We should look at the total dimension of y times cos, right?
Total dimension of y times cos is always 2. Okay? That's how you define the dimension of y. Because when you scale this, this has a particular dimension, and then this absorbs the rest of the dimension. Okay? So basically now we have it. Okay? We just have to do a little bit more work to figure out what happens near the space transition. But we almost have it now. So we know that as long as pi j is bigger than 2, that means low temperatures, right? Low temperatures, vortices are irrelevant. And therefore the old theory that we had was correct. But when pi j becomes less than 2, this guy is relevant, and then we want to figure out where it goes, right? Once something is relevant, you have to follow the flow and ask where it goes. Okay, so it's going to flow to strong coupling, right? And now you ask what happens in strong coupling. And that is what we'll talk about tomorrow. Okay? So basically I have to show you that a strong coupling, the e to the I theta e to the minus I theta parameter actually decays exponentially with distance, not like a power law. Okay? Questions?
So, if you go to this linearized model,
Yeah.
we started. So, see, as someone mentioned before, also the action is not invariant under the.
That's correct. It's a partition function that's invariant.
Yeah, but action should be invariant.
Why? What are you really measuring anyway? You're measuring correlation functions, right? So correlation functions should be invariant. Where did you get this idea that the action should be invariant?
The action is invariant if you transform it, right? You just say that you have a different transformation law.
Right.
Right? M is also being transformed.
Yeah.
Then the action is invariant.
So measure in some sense.
Yeah, measure is invariant. Of course.
If the action is invariant under M, then M plays nothing. Then all of this will fall. That's back to work. M have to do something. Right? M have to contribute to the energy functional so that you want the minima.
Just to mention something in
Yeah.
that regard, that M actually has a gauge degree of freedom. Like
Yeah.
M can have a gauge transformation,
Correct.
which does not change anything.
It doesn't change Q. That's right.
Doesn't change Q. So, so what I'm saying that in the action, the linearized action that we wrote down, actually every transformation of theta corresponded with a transformation in N. So it keeps actually the action invariant. And that is exactly.
That's what Ashok was saying. That if you take if you transform M as well as theta, then it remains invariant. But really, look, it's correlation function that you're trying to compute, right? So, as long as the correlation functions are invariant, I'm happy. Okay, other questions?
So we started with this linearized model which had a much larger Hilbert space as compared to this XY.
Much larger configurations, set of configurations, correct? Yeah.
So then by restricting QR to be 0 and plus minus, we are again restricting these configurations.
Correct. Yeah, we are restricting them back. The claim is that as long as some model, it doesn't matter what the Hilbert space is, right? Even if you think of a quantum model, as long as the symmetries are the same, okay, then really the critical phenomenon has to be the same. So think of different kinds of Ising models, okay? There are Ising models which are, usually in solid state physics, Ising models come about because there's some easy axis anisotropy of some spin, right? That spin could be 1/2, it could be 3/2, it could be 5/2, it could be anything. So the underlying Hilbert space of those spins is very different. But the symmetries of the energy function or the Hamiltonian are the same. And therefore the critical phenomena has to be the same. Okay, that's the whole point of view of RG. Okay, of course the details of the short distance physics will be very different in those different models. If you're looking for the critical phenomena, then they have to be this way. Okay? Yeah.
So generally,
Yeah, actually, this correlation function. Okay, how we determine this dimension and this anomalous dimension. Okay.
Yeah.
This result we got, the theory was very different from this theory, sine-Gordon.
No. I'm just trying to say that supposing I want to perturbatively evaluate this guy,
Oh, okay.
whether this is relevant or irrelevant.
Okay.
So I'm thinking about a fixed point, which is that.
Okay.
And that's my fixed point. Around that fixed point, I want to see if this operator is relevant or not.
Okay.
Okay, for that purpose, I need to compute correlations on that, around that fixed point. And that's what this is. Right? So it's totally legitimate. As long as y is irrelevant, everything is good.
Yeah.
Because it flows back to y equals 0, and then that fixed point is in fact stable. Okay? And tomorrow we'll find out what happens when it flows away.